students, welcome to this lecture, and in this lecture we will focus our study towards the geometrical say behavior of the system of linear equation, geometrical behavior of the solution of dynamical system. Now for simplicity we restrict our discussion for n equal to 2, means we are considering the system x dash equal to f of x, where x is 2 cross 1 vector, and we try to, because it is we need to represent on your xy plane. So that is why we restrict ourselves to n equal to 2 itself. So it means that we are considering the following system of differential equation: dx by dt equal to f of x comma y and dy by dt equal to gx comma y here. And if we consider that f and g are nice enough, in the sense that f and g have say partial derivatives with respect to say x and y, and if they are continuous, then we can talk about the solution of system 1. And we may notice that every solution of 1 solutions are given as xt comma y of t, where t is belonging to some interval. Then this xt and yt trace a curve in 2 dimension as well as in 3 dimension. So if you look at, as t is running from I over I, then xt and yt will trace a curve in 3 dimension plane, that is t comma x comma y. So let us take an example and then try to understand this. So consider the following set of differential equation: dx by dt equal to y and dy by dt equal to minus of x, and this we can solve here, and we can simply say that it is nothing but d2x by dt square is equal to dy by dt, and this is nothing but equal to minus of x. So d2x by dt square plus x equal to 0, and we know the solution of this: xt is equal to c1 cos of t plus c2 sin of t, and similarly we can find out yt as minus of x. So we can simply say that it is nothing but c1 sin t plus minus c2 cos of t. So I can take any of the solution here. So in particular I can take that xt equal to say cos of t here, and yt equal to sin t is one particular solution of this system of differential equation. So xt is equal to cos t. So is it a solution here? So we can take so solution xt, we can take sin t and yt equal to cos t if we impose certain condition, initial condition on this system. So let us take a particular solution of system 2, that is xt equal to sin of t and yt equal to cos of t. So it means that we are putting certain initial condition along with this. Now these curves, as t belongs to some interval say I, trace a curve in 3 dimension. If you look at here and represent this as x, y, and this is t here, then as t is running from some a to b, this will trace like this kind of path here, right? This is kind of a helix in 3 dimension plane here. So so it means that for t belonging to this I, this will trace this kind of a path here. Now the interesting part is this, that this sin t and cos t, this solution will also trace a path in 2 dimension plane, like in xy plane. If you consider here that t is running in some interval say I, for the time being let us take this interval as say 0 to 2 pi kind of thing. So close interval 0 to 2 pi. Then we can say that as this is also this is kind of a traversing a path in your 3 dimension plane. But if you consider that if you look at the projection of this 3 dimension figure into xy plane, then it is basically, say it is like this here. So it means that if we can remove this, and here since we have xt equal to sin t and yt is equal to cos of t, then we can simply say that x square t plus y square t, which is nothing but sin square t plus cos square t, and this is coming out to be 1 here. So, it means that that not only this solution curve trace a curve in 3 dimension, but it is also tracing a curve in 2 dimension plane x y, and the curve it is given by x square t plus y square t equal to 1 here for all t belonging to this interval I. So, it means that the trace curve C in xy plane has a special name, and we call this curve as trajectory or orbit of the solution x and y here. So, we define the orbit path or trajectory as follows. The orbit which is also known as path or trajectory of a solution x t comma y t is the curve traced by the solution in xy plane, and xy plane is also known as phase plane. And so, it means that, so here we are not considering the say curve in 3 dimension, we are simply saying that what is the projection of the curve onto xy plane, and we are calling that projection as orbit of the solution x t comma y t here. And now let us consider few example by which we can consider the orbit of the few system of differential equation. So, first one is dx by dt equal to y and dy by dt equal to minus of x, and if you look at this is similar to the previous problem. In fact, it is the same as previous one, and here we can say that the orbit is given as x square plus y square equal to 1 here. So, orbit of this system of differential equation is given by dx by dt equal to y, dy by dt equal to minus x as x square plus y square equal to 1 here. Okay. Now, look at the second equation, dx by dt equal to minus x minus y, dy by dt equal to x minus y, and so here to we can simply say that how we can solve this. It is nothing but x y dash is equal to minus 1 minus 1, 1 minus 1 here, x and y here, and we want to find out the solution here. So, we can find out the solution of dx by dt equal to y and dy by dt equal to minus x as follows. We can simply say that d2x by dt square is equal to dy by dt, and this is nothing but minus of x from second equation. So, we can write d2x by dt square plus x equal to 0, and we can find out the solution x t equal to c1 cos t plus c2 sin t, and y is nothing but dx by dt. So, y can be written as minus c1 sin t plus c2 cos of t. Now, so this represent the general solution of this system of differential equation. Now, if you impose certain initial condition, for example, let us say that x y at 0 0 it is equal to say 0 1, then we can find out a particular solution here. So, we are imposing condition that x of 0 equal to 0 and y of 0 equal to 1, and we can say that let us say that initial condition solutions is given as x t equal to sin t and y t equal to cos of t here, and so here this will trace a helix in 3 dimension, and so it means it will trace like this kind of a path here. So, it is a helix in t comma x comma y plane, and not only it trace a path a curve in 3 dimension. If you consider the projection onto xy plane, then it will be a kind of a circle on xy plane. So, if you basically you have a helix and then you simply put it down to on xy plane. So, you paste it together. So, when you paste it together, it will form a circle which is given as x square y square x square plus y square equal to 1, and that you can find out as you can say x t equal to sin t, y t equal to cos t. You can find out say x square t plus y square t equal to 1 here. So, it means that this will form a circle on xy plane, and that will represent the say curve traced by solution on the xy plane as t running over some interval I here. So, for the time being let us take this interval as some 0 to infinity. When t is starting from 0 to infinity, it keep on moving on this circle infinitely many times. Okay. So, it means that the curve traced by the solution as t is over I is known as the orbit of the solution in the xy plane, and the xy plane is known as phase plane. So, here now considering the second problem, dx by dt equal to minus x minus y, dy by dt equal to x minus y, and some initial condition. For example, let us take initial condition x 0 equal to 1 and y 0 equal to 1. Then this second system can be written as this system x y dash equal to minus 1 minus 1 1 minus 1 x y, and this we have already discussed how to find out the solution, and solutions are given as x t equal to e to power minus t cos of t, y t equal to e to power minus t sin of t here. Now, it will say again give you a helix kind of a figure in 3-dimension picture. The only thing is that as t tending to infinity, your your solution is merging towards 0, or you can say it is something like this figure. So, here we have this, then here it is started from 1 and then this radius is keep on decreasing. So, this is a kind of a helix kind of a figure. The only thing is that the radius is you can get it here, the radius is basically tending to 0 as t tending to infinity. So, it means that here this will trace a helix kind of a figure in t comma x comma y plane, and if you project everything on x y plane, it will give you a spiral kind of a figure. It is something like this, either like this, sorry, it is the other way around. So, it is like this, or it is something like this, say it is something like this, right. So, now the direction will depend on the equation, that is whether this will this or this. So, whether it is coming like this or it is coming like this, it is clockwise or anti-clockwise, but ultimately it is coming out to tending to 0 as t tending to infinity. In fact, that we can look at here, it is x square plus y square is equal to e to power minus 2 t cos square t plus e to power minus 2 t sin square t here, or this we can write it e to power minus 2 t. So, your x square plus y e square is equal to e to power minus 2 t. So, it means that as t tending to infinity, it will trace one of the figure like this. Now, let us check, it will be exactly which one of the figure. So, that we can verify from the equation. So, first thing we get from the solution curve is that x square plus y square equal to e to power minus 2 t means as t tending to infinity, your solution will tend to 0 here. Now, let us look at the direction here. So, direction will be what? Just take one point here. So, it is one point on here, it is your x naught is something, y naught is simply 0 here. So, it is something x naught comma y naught here. So, if you look at dx by dt at this particular point x naught y naught. So, at this particular point dx by dt equal to minus x naught. So, at this point your dx by dt at x naught comma 0 is equal to minus x naught, and dy by dt at x naught comma 0 is nothing but x naught here. So, here we can say that dx by dt is decreasing and dy by dt is increasing. So, it means that dx by dt is decreasing means your x is decreasing. So, it means x will be lower down and y will be increasing. Okay. So, if you look at this will be what, suppose your point is x naught y naught here. So, x naught is decreasing, y naught is increasing. So, here y naught increasing means if y naught is 0, so it means increasing means it will go into a positive value. So, at t is starting from this point onward, it will go to something positive. So, it is something like this figure. right. So, here your the direction of the curve will be going anti-clockwise, right. So, here if you look at this, here your y naught is moving say downward. So, it means that here y naught is negative. So, it means that dy by dt is decreasing, but here we have discussed that dy by dt is increasing. So, this will not give you the say orbit of the system dx by dt equal to minus x minus y and dy by dt equal to x minus y. So, it will give you a figure like this, right. So, this figure is known as spiral like figure. We will consider more about this in coming few lectures. Now, in the third third part, dx by dt equal to a and dy by dt equal to b. So, solutions are constant solution, dx by dt equal to we can simply say that solution is say ax aat plus some constant x naught some constant C1 and y equal to Bt plus some constant C2. We can fix your this C1 and C2 provided that let us say that x0 equal to x naught, right. So, at t equal to 0 your C1 is given as 1. So, x is equal to At plus 1 and y equal to Bt plus 2. So, this will give you if you remove your t from this, you can remove it and you can get a relation like y equal to mx plus c kind of a thing. So, in this case, in the third case, your orbits basically follow some kind of a line and it is originated from 1 and 2. So, it will form a line which is starting from 1 2 and somewhere going up to this. So, it means that the orbit in third example is a line originated from 1 comma 2 and orbit in the second is nothing but a spiral converging to 0 and the orbit in the first case is basically circle of a radius 1 here. Now, here everywhere we have imposed initial condition x naught and y naught having certain different value. Now, if you remove your initial conditions, then it will give you say all possible path traced by the solution curves here. For example, if you look at the first case dx by dt equal to y and dy by dt equal to minus of x, then here your initial conditions gives you that this orbit of this solutions is basically unit circle x square y plus y square equal to 1, and if you take any arbitrary initial curve, then it will give you the family of circles as a trajectory as a path traced by the solutions of dx by dt equal to y and dy by dt equal to minus of x. Now, here we say that in all these problems we are able to find out the orbit by solving the system first and then removing the parameter t. Now, we simply say that one very important say benefit of considering the orbit is that we can find out the orbit of the solution x equal to xt and y equal to yt without solving the system of differential equation. In fact, the orbit of the solutions x equal to xt, y equal to yt are the solution curve of the first order scalar equation dy by dx equal to gxy divided by f of xy. Therefore, to find the orbit we need not to find solution of the system here. Please look at here what we are doing here. We have x dash equal to f of x comma y and y dash equal to g of x comma y here. So, here we are getting the solution xt and yt here, and this will trace a curve in tx comma y comma t comma x comma y plane. And here we simply say that orbit means we are finding a relation between the solution component, that is x and y, without say considering the parameter t here. It means that we are finding a relation between the solution component xt and yt. Now, here we simply say that this is what, this is dy by dt equal to g of xy and dx by dt equal to f of x comma y. Now, we can consider that y is a function of x here, y is a function of x when we considering the orbit here. So, orbit is the relation between solution component. Now, when we say that we are finding the relation between xt and yt, it means that we are assuming that either y is a function of x or x is a function of x. So, it means that I can consider this as say like let us say without loss of general, let us assume that y is a function of x here. Then we can find out the dy by dx as dy by dt divided by dx by dt here. So, it means that I can write this as dy by dt is given as g of x comma y and dx by dt is given as fx comma y here. So, it means that I can find out a relation between y and x provided that dy by dx equal to gxy divided by f of xy has a solution. Now, the solution curve of this scalar differential equation, first order scalar equation is known as your orbit. So, here the one good thing happened here, that here we can find out the orbit of the solution without actually finding the solution of the system x dash equal to f x y and y dash equal to g x comma y here. So, it means that therefore, to find the orbit we need not to find solution of the system here, and that is one good thing about the orbit of the solutions here. So, let us take one example and find out the orbit. So, find the orbit of the system of differential equation dx by dt equal to 2y into 1 plus x square plus y square, dy by dt equal to minus x 1 plus x square plus y square. So, if you look at in previous few examples, we have considered certain system of differential equation which are quite easy to solve. But if you consider this kind of a system of differential equation, it is not very easy to find out the solution of this system of differential equation. But still, with the help of this we can find out the orbit of the solution of this system of differential equation as follows. We simply calculate dy by dx equal to gxy, that is minus x 1 plus x square plus y square divided by 2y 1 plus x square plus y square. Now, this 1 plus x square plus y square is never 0. So, we can cancel out and we can have dy by dx is equal to minus x upon 2y, and it is basically a separable equation. So, we can write 2y dy plus x d of x equal to 0 here. So, we can say it is y square plus x square by 2 plus equal to some c, let us say that c square, and we can say that this is nothing but the ellipse equation. So, we can say that the orbits of the system of differential equation is given by ellipse, where c is some arbitrary constant. So, c is some arbitrary constant say r. So, orbits here is the ellipses for c is some number in r. Now, here very important thing we need to note down, that a solution curve of the differential equation represent an orbit provided that both dx by dt and dy by dt are not simultaneously 0 along the solution. So, here if it happen, so here we are assuming that this dy by dt or dx by dt, because this expression dy by dx equal to gxy upon fxy makes sense provided that this fxy is non-zero. And similarly, we can consider that in place of this I can consider dx by dy as f of xy divided by g of xy. So, it means that here we are assuming that gxy is non-zero. So, if we are finding the orbit by this, that dy by dx equal to gxy upon fxy, we are assuming that f is non-zero, and if we are using this differential equation dx by dy equal to fxy upon gxy, we are assuming that g is also non-zero. So, it means that we can use this procedure to find out the orbit provided that none of the function f and g are 0 at the same time. So, it means that simultaneously dx by dt and dy by dt are not 0. It means that if it happened, if a solution curve contains an equilibrium point of 1, equilibrium point means where fxy is equal to 0 and gxy equal to 0, then the whole solution curve is not an orbit. Basically, in this case the orbit, the solution curve is basically the union of several distinct orbits. So, let us look at this concept here. If you look at the consider the system of differential equation dx by dt equal to y into 1 minus x square minus y square, dy by dt equal to minus x into 1 minus x square minus y square, and if you find out the orbit of this, so we can simply say that dy by dx equal to minus x upon 1 minus x square minus y square divided by 1 minus x square minus y square here. So, here we are using this thing that dy by dx equal to gxy upon fxy here. So, here when you simply say that if we assume that 1 minus x square minus y square is non-zero, let us assume this, then I can write this as dy by dx equal to minus x upon y, provided that 1 minus x square minus y square is non-zero. If it is non-zero, then we can find out the solution here y dy plus x dx equal to 0. So, it means that it is x square plus y square equal to c square. So, orbits are given as x square plus y square equal to c square, and c is some constant here. But if we take that c is equal to 1, then it is what? The orbit is nothing but x square plus y square is equal to 1. So, one of the orbit corresponding to c equal to 1 is coming out to be x square plus y square is equal to 1, but this x square at x square plus y square equal to 1, this dx by dt is equal to 0 and dy by dt is also equal to 0. So, it means that the x square plus y square equal to 1, if I look at this, that at each point on this unit circle your dx by dt is 0 and dy by dt is also 0. So, it means that here we are getting a constant solution, and constant solution will not trace any path other than the point itself. So, it means that on the unit circle every point is an orbit, because it will not trace any path other than the point itself. So, it means that here the orbit of the system of differential equations are x square plus y square equal to c square, where c is not equal to 1, and the point on the unit circle x square plus y square equal to 1. So, it means that your system of orbits of the system are given as x square plus y square equal to c square, where c is not equal to 1, and all point on the circle x square plus y square equal to 1. So, basically you take any circle here, then it will be an orbit, but if you consider the unit circle, then every point on this basically act as an orbit here. So, here we have infinitely many orbits available for the system of differential equation, right. So, here because on this orbit in this orbit we have an equilibrium solution. So, in this x square plus y square equal to 1 is not a single orbit, but it is a union of infinitely many different orbit. So, that will give you the orbit of the system given here. Now, look at the orbit of the system of differential equation dy by dx by dt equal to y square and dy by dt equal to x square. So, again if you find out dy by dt is equal to dy by dx is equal to x square upon y square, and you can say that y square dy equal to x square dx here. So, we can say that y cube upon 3 is equal to x cube upon 3. You can consider this as you can simply say that x cube by 3 plus some constant here. So, we can simply say I can simply write it as y equal to the x cube plus c by 3, you can consider x cube plus c upon 1 upon 3 here. So, y can be written as x cube plus c upon 1 by 3. So, orbits are given by this. Now, if you look at here that if c is non-zero, it will give you an orbit y equal to x cube plus c upon 1 by 3. Now, if I take c equal to 0, then what you will get? You will get y equal to x here. So, it means that this y equal to x is also an orbit corresponding to c equal to 0, but this orbit contains a say so this is this line, but this contains a point 0 0, and at 0 0 we have a equilibrium solution of this. So, it means that this y equal to x cannot be a single orbit, rather than it is a union of three different orbit, that is y equal to x when x is less than 0, y equal to x when x is greater than 0, and the point x equal to 0 and y equal to 0 here. So, it means that all these curve y equal to x cube plus c to power 1 by 3 where c is not equal to 0 is your orbit, and corresponding to c equal to 0 y equal to x is not a single orbit, rather than it will be a union of different orbit because it contained an equilibrium solution. So, if it is an equilibrium solution, this will not trace any other point other than 0. So, here 0 is contained on this orbit. So, this orbit is not a single orbit, rather than it is union of different orbits. So, union basically it is y equal to x when x is less than 0 means this line, and y equal to x when x is positive this line, and the origin point itself. So, the orbit in this case are the curve y equal to x cube plus c, c non-zero, and y equal to x when x is less than 0, y equal to x when x is greater than 0, and origin itself, that is x equal to 0 and y equal to 0. So, by this we can find out all the orbits of the system of differential equation. Now, it may happen in general that we may not able to solve the system dy by dx equal to fxy upon gxy. In fact, we are able to find out the orbits by solving this equation dy by dx equal to gxy upon fxy, and we know that it is quite difficult to find out the solution of this system, this scalar differential equation 3. So, it means that what happen if this is not solvable, right, solvable in the sense that we are not able to find out the solution in explicit form, and still we will be able to describe the orbits of one with the help of direction field. What is this? If you look at dx by dt is what? Dx by dt is equal to fx comma y, and dy by dt is equal to your gx comma y. And if you look at, this is the velocity component in x direction and this is the velocity component of y direction. I can write it, this is Vx and this is Vy. So, it means that if you start with any point, let us say this is your point, and at this point it correspond to some t equal to some t naught. So, at t equal to t naught, you know what is the velocity along the x component and what is the velocity along the y component. So, Vx is Vy and the total velocity is given as Vx square plus Vy, sorry, this is Vx square plus Vy square. Let me erase this. So, it is Vy square. So, it means that velocity at every point is given to you. So, when you have this point, you know how to proceed further, and when you have this thing at this point, your t is corresponding to say t1, and again you can calculate your Vx and Vy at t1, and again you have some point, some direction to go, and then in this way we can find out different direction at a given point, and using this we can trace out your orbit in 2 dimension without solving your system dy by dx equal to say gxy upon f of x comma y here. So, here when we are not able to solve in a explicit form, then we can look at the direction field set up by this dx by dt equal to fxy and dy by dt equal to gxy, and we can still have the exact say description of the orbit generated by the solutions of this. And the and in this way this notation of the orbit can easily be extended to the higher dimension case also. It means that if we have higher dimension case, means we have dx1 by dt equal to f1 say x1 to xn and up dxn to dt equal to fn x1 to say xn. Then as we have pointed out here, then here also we have say velocity component v1 to vn, and the total velocity is given as under root v1 is square to vn is square, and each point you can find out the velocity and the direction using this. So, it means that just generalizing this concept, we can have the say notion of orbit in higher dimension also. So, in this lecture we have discussed the concept of orbit, which is the curve traced by the solution component in x y plane if it is 2 dimension, and in x1 to xn plane if it is n dimension plane. So, basically orbits are the relation between the solution component, and we have discussed certain method to find out the orbit of the system of differential equation. And in next class we will discuss some more cases to find out this orbit and some properties of orbit here. So, with this I end this lecture, we will discuss in next class. Thank you very much.